If you watch anyone talk about their automation setup, you hear about the AI model they picked, the fancy agent framework they are trying, the clever prompt that made everything click. Nobody talks about the layer underneath all of that. Nobody makes a video about the thing that actually keeps the whole setup from falling over on a busy afternoon. And that thing is about as unglamorous as software gets. It is a queue and a scheduler. I have been running these things quietly in the background for a while now, and every time something in my setup goes wrong, the fix almost always comes back to one of two things. Either there was no queue when there should have been, or something was not scheduled properly. So today I want to pull the curtain back on this boring backbone, explain what it actually is in plain terms, and tell you why it is the piece that lets me trust AI automations to run without me watching them. Why the flashy stuff breaks without this. The impressive parts of any automation setup are easy to point at. The agent that reads your files and answers questions. The pipeline that writes a script and renders a video. The workflow that fires off 10 tasks at once. Those are the things people screenshot and share. But here is what those screenshots never show you. What happens when two of those impressive jobs try to run at exactly the same time? What happens when a job starts, hits an error halfway through, and just quietly disappears? What happens when the thing that was supposed to run at midnight simply did not run because the machine was busy? The flashy layer does the interesting work. The queue and scheduler layer is what keeps the interesting work from quietly eating itself. Without it, you do not have a reliable automations. You have a fragile demo. What a queue actually is. I want to start with queues because they are the simpler idea of the two, and because I have a concrete example sitting right in my own setup. A queue is just a line. Jobs go into one end, they come out the other, and only one job runs at a time. That is it. The reason this matters is not complicated. Some jobs are heavy. They use a lot of CPU, a lot of memory, a lot of disk. My video render is a good example. Rendering a finished video is one of the most demanding things my machine does. It pegs the CPU. It uses the graphics card. It writes large files fast. If two renders tried to run at the same time, they would fight over every resource on the machine. The result would not be two videos rendered in half the time. The result would be two broken renders, a locked up system, and probably a crash. So my render pipeline enforces a queue. Every video job goes into a list. One job runs. When it finishes, the next one starts. It sounds almost too simple, and that simplicity is exactly the point. The render queue example in plain terms. My actual render queue is a JSON file on disk. When a new video job is submitted, a small script appends a record to that file. A separate process checks the file on a loop. If a job is waiting and nothing is currently running, it picks up the next job and starts it. When the job finishes, the record gets updated. The next loop iteration picks up the one after that. There is no magic, there is no fancy framework. There's a file, a loop, and a flag that says whether something is already running. You could write the whole thing in a couple dozen lines. The reason it works is not sophistication, it is discipline. The queue enforces one thing at a time, and that single rule prevents an entire class of problems. What a scheduler actually is. The other half of the backbone is the scheduler. Where a queue is about ordering jobs that arrive at unpredictable times, a scheduler is about jobs that should happen at predictable times, every night at midnight, every Monday at 9, the first of every month. These are the jobs that should just happen without you remembering to trigger them. In my setup, backups are scheduled. My encrypted offsite backup runs every night at a fixed time. I do not think about it, I do not trigger it, it just runs. Published jobs are scheduled. Videos go out on a cadence, one per day per channel, and the scheduler fires the right job at the right time. Analytics polls are scheduled. Health checks are scheduled. Once something is on the scheduler, it disappears from my mental load. I do not track it, I do not worry about it, and if it stops running, I find out from a log or an alert, rather than from a customer noticing a problem. Run is the simplest scheduler. If you are on a Unix-based system, the simplest scheduler available to you is cron. You write a line that says, run this command at this time, and the operating system handles the rest. On Windows, there is the task scheduler, which does the same job with a different interface. The point is not the tool, the point is the concept. Time-based jobs need a home. They need to be registered somewhere that will fire them reliably, at the right time, whether you are awake or not, whether you are thinking about them or not. A sticky note reminder to yourself is not a scheduler. A calendar entry you might miss is not a scheduler. A registered job that the operating system runs whether your coffee is ready or not, that is a scheduler. The difference between those two things is the difference between an operation that runs itself and one that depends on you. Now the patterns that make it trustworthy. Having a queue and a scheduler is a start, but a queue that loses jobs is worse than no queue, because at least without a queue you know what failed. A scheduler that silently skips jobs is dangerous for the same reason. So once you have the basic structure, you need 4 patterns that make it actually trustworthy. I want to go through each of them in plain terms, because the names sound more complicated than the ideas are. These 4 patterns are idempotency, locks, retries, and a place for failed jobs to land. Together they are what let me close my laptop and trust that the things running in the background will either succeed or tell me clearly that they did not. Idempotency means safe to run twice. The first pattern is idempotency. That word sounds intimidating, but the idea is straightforward. A job is idempotent if running it twice produces the same result as running it once. In other words, it is safe to repeat. Why does this matter? Because in any real system, you will sometimes run a job more than once by accident. A retry fires before the first run confirmed it finished. A scheduler fires on a slow machine and the previous run is still cleaning up. An operator kicks off a job manually, not knowing it already ran. If the job is not safe to repeat, you end up with duplicates, corrupted data, or a half-done state that is hard to clean up. If the job is idempotent, running it twice just does the same correct thing twice. The practical way to build this is to have jobs check before they act. Before uploading a file, check if the file is already there. Before inserting a record, check if it already exists. Before sending a message, check if it was already sent. It adds a little code and it removes a whole category of painful bugs. Locks stop 2 copies running at once. The second pattern is locks. A lock is just a flag that says, this job is already running, do not start another copy. Without a lock, a scheduler can fire a job, the job runs long, the next scheduled time arrives, and the scheduler fires it again before the first one is done. Now you have 2 copies of the same job running against the same data at the same time. Even if each copy is correct on its own, 2 copies running together can corrupt each other. A lock prevents the second copy from starting. The simplest version of a lock is a file. When a job starts, it writes a small file to disk. When a second copy tries to start, it checks for that file first. If the file is there, it exits. When the first copy finishes, it deletes the file. That is a file-based lock, and it works well enough for most single machine setups. For jobs running across multiple machines, you need something shared, like a record in a database, but the concept is identical. One job at a time, enforced. Retries handle the failures that are not your fault. The third pattern is retries. Some failures are permanent. You tried to write to a path that does not exist, the file you needed was not there, the input was malformed. Those should not be retried, they need to be fixed. But a lot of failures are transient. The network blipped for a second. An external service returned an error because it was momentarily overloaded. A file was locked by another process and would have been free 30 seconds later. These failures are not bugs, they are just noise. Without retries, every transient failure looks the same as a real failure. Your job queue fills up with error logs for things that would have worked fine if they had just tried once more. With retries, the job waits a short time and tries again. Most transient failures resolve on the second or third attempt. The ones that do not are probably real problems worth looking at. The key is to limit retries and space them out. You do not want a job hammering a broken external service 100 times in a row. 3 attempts with a short wait between them is usually enough. Where failed jobs land. The fourth pattern is what I call a landing place for failed jobs, which in technical writing gets called a dead letter queue, but you do not need to remember that name. The idea is simple. When a job fails all of its retries and is genuinely stuck, it should not just vanish. Vanishing is the worst outcome. If a job silently disappears, you have no idea it failed. You have no way to look at it, understand what happened, retry it manually, or alert on it. A landing place is just a separate list where permanently failed jobs go. They sit there, clearly marked as failed, with whatever error information they logged. You can check this list on a schedule, alert on it, or review it manually. The important thing is that nothing is lost. Every job either succeeds or it ends up somewhere you can find it. That completeness is what lets you trust the system. If something is missing, you go check the landing place. It is either there or it succeeded. There is no third option. Why this is what lets AI automations run unattended. I want to connect all of this back to why it matters specifically for AI automations, because I think this is the part that does not get said enough. AI jobs are often slow, expensive, and hard to restart cleanly. A video render might take 20 minutes. A transcription job might call an external API and cost real money. A batch processing job might touch hundreds of files. These are not the kind of jobs where you want to find out at the end of 3 hours that it failed in the first 5 minutes and no one noticed. They're also the exact kind of jobs where two copies running at once causes real damage, double charges, duplicate files, partially processed data that looks complete but is not. The queue and scheduler patterns I have described are not theoretical best practices for enterprise systems. They are the practical minimum for running heavy AI jobs on a single machine with any confidence. They are what let me start a job, close my laptop, and expect a finished result rather than a mystery. The setup does not need to be complicated. I want to be clear that I am not describing a complex infrastructure build. I am describing a JSON file, a loop, a log file, and a couple of cron entries. The whole thing that I use today started as something I wrote in an afternoon. It has grown a little since then, gotten a few more safety checks, but it is still fundamentally simple code. The point is not to build something impressive. The point is to have the discipline to add these patterns before the problems they prevent become obvious. Because when a job queue goes wrong, it usually goes wrong in a way that is annoying to debug and embarrassing to explain. A double publish, a missed backup, a corrupted output. The boring fix is to have the boring layer in place before that happens. Trusting the unattended work. At the end of the day, the whole reason I spend time on this plumbing is so that I can trust my own setup to do things while I am not there. That is the promise of automations. Not that it makes things faster while you watch, but that it keeps doing the right thing when you step away. The AI layer gets the credit because it is the part that feels intelligent. But the layer that makes it trustworthy is the queue that stops jobs clobbering each other, the scheduler that fires things at the right time, the idempotency that makes reruns safe, the lock that prevents duplicates, the retry that survives a blip, and the landing place that makes sure nothing silently vanishes. Every time I trust an automated job to run overnight, I am trusting that boring layer, and it earns that trust by being completely uninteresting and completely reliable. If you want more honest behind-the-scenes looks at how a real automation setup actually holds together, subscribe and follow along. Thanks for watching, and I will see you in the next one.